Continue with the derivation of work done required for reciprocating compressor. In this one we have neglected the assumption we have to. Number 1 is that there is no bouncing of the suction and delivery valve. So, from 4 to 1 we have suction process takes place at constant pressure P1, and unless and until mentioned P atmospheric equals to P1. Similarly, from 2 to 3 is delivery, and during this process we assume that the delivery pressure equals pressure, receiver pressure equals to P2. Similarly, we assume that the 4 to 1 is suction stroke, and during this stroke there is no heat transfer. So, Q14 equal to 0. Heat transfer is 0 only when we have a temperature equal to constant. So, T1 equals to T4. 2 to 3 is the delivery stroke. During this again we assume the heat transfer equals to 0, and therefore, we assume the temperature T2 equal to T3. Third assumption we make is that the air is an ideal gas. So, it satisfies the ideal gas equation, that is PV equals to MRT, and the compressor is modeled as steady flow. The compressor is modeled as steady flow device, that is work done is given by for non-flow process is integral minus VdP. At point 4 the suction valve opens, and at point 1 the suction valve closes. The mass of air inducted will be M1 minus M4. The mass at M4 is same as the mass at 3. So, we will first calculate what is the mass of at point number 4, that is called as residual mass. The pressure at point number 4 is P1, volume is V4, gas constant is R, and temperature is T1. At the end of the suction stroke, the mass in the cylinder M1 equals to the pressure at point number 1 equals to P1, volume is V1, R, T1. I have written here T4 equal to T1 because my assumption is that T1 equals to T4. So, net mass inducted will be equals to M, that is a fresh charge, equals to M1 minus M4. So, M1 we will replace as P1 upon RT1. This is a common quantity between M1 and M4, and we will have V1 minus V4. So, this is a fresh mass inducted in one cycle of a cylinder. To find the mass flow rate, we will multiply M by number of revolutions per second. So, the expression for M dot will be P1 upon RT1, that is the density multiplied by volume is V1 minus V4. So, density multiplied by volume is mass multiplied by N by 60 kg per second. Single acting or double acting, according to that you will take the care of the equation. So, we have an equation equals to N acting equals to 1 for single acting, and N acting equal to 2 for double acting. So, your equation becomes P1 into V1 minus V4 upon RT1 into N by 60. This one is universal equation, can be applied for single acting as well as for double acting. Two equation, one is M dot for single cycle is P1 RT1 P1 minus V4, and M dot equals to number of acting into P1 V1 minus V4 RT1 into N by 60. This one is a mass flow rate, and this is a mass, this is a fresh mass inducted. To find out this work done, we require the area of 1, 2, 3, 4. 2, 3, 4, we will consider here one point, that is A point, and we consider here B point. So, we can calculate the 1, 2, 3, 4 area as area 1, 2, A, 4, 3, A, B. The first figure represents reciprocating compressor with clearance. In the second figure, I want to calculate the area 1, 2, 3, 4, that is the required work. I can calculate this work or theoretical work. I can find out that area by considering 1, 2, A, B, that is this area, B, 4. What we observe here is that at the end of the delivery stroke, we don't have volume. It means that the TDC will lie at this point and the BDC at this point. So, this figure to calculate this work done, let make a generalized process, that is this is P to the power N. The work is given by the equation equals to W integral of minus VdP. To solve this equation, we must replace V in terms of constant C. So, we have a polytropic process. So, index is P to the power N equal to constant. To solve for V, we make it here V to the power N C divided by P. We shift this index to this side, which we get V equal to C by P to the power 1 by n. Finally, we get V is equal to C to the power 1 by n, and P in denominator will shift as P into to the power minus 1 by n. We will put this value of V in this equation. We get equals to my integral minus C to the power 1 by n P to the power minus 1 by n dp. Now C is constant, that is why we taken C to the power minus 1 by n integral of P to the power minus 1 by n dp. Integral of P to the power minus 1 by n is minus 1 by n plus 1 upon minus 1 by n plus 1. So we get C to the power minus 1 by n P to the power minus 1 by n plus 1 upon minus 1 upon n plus 1. 1 upon n plus 1 is same as n minus 1 plus n, which can be written as n minus 1 upon n. So we get W equals to minus C to the power 1 by n upon n minus 1 P to the power n minus 1 upon n from P1 to P2. We want to solve this by putting upper limit and lower limit. What we get is minus C to the power 1 by n upon n minus 1, upper limit is P2 and lower limit is P1. What we do is now we shift this C inside. So we get minus n upon n minus 1 C to the power 1 by n P2 as it is minus C to the power 1 by n P1 to the power n minus 1 upon n. To solve this further, we can replace this C as P2 V2 to the power, whole thing is again power 1 by n multiplied by P2 to the power n minus 1 by n. Now this C will be replaced by P1 V1 to the power n. C is replaced by P1 V1 to the power n to the power 1 by n, and now we write the same term as P1 to the power n1 minus 1 upon n. What we get is W minus n upon n minus 1. This V to the power n by to the power n, and this is 1 by n will be cancelled, is V2. We have P2, the P2 power is 1, and we will get P2 to the power 1 by n, and this also base is P2 to the power 1 by n. So we have 1 upon n plus n minus 1 upon n. Our base is same, so we can write this as 1 plus n minus 1 upon n. Plus minus 1 is cancelled, n upon n is also 1. So we simply left with P2, and same term we get here also P1 V1. So we will rearrange this term and we write this as minus of n upon n minus 1 multiplied by P2 V2 minus P1 V1. Negative quantity P2 is very high value as compared to V2, so this whole quantity is negative. So this one is negative work. So work required to dry compressor, we just forget the sign minus. So this is the work of compressor is n upon n minus 1. We will take out P1 V1 outside the bracket because normally we supply the suction conditions. So we get P2 V2 divided by P1. So we can very well apply the polytropic equation from 1 to 2, that is P1 V1 to the power n equals to P2 V2 to the power n. We will solve for this ratio V2 by V1. V2 by V1 is P1 by P2 to the power 1 by n. We will change the reciprocal, change this sign, we get P2 by P1 to the power minus 1 by n. So we replace this V2 by V1 with the value of P2 by P1 to the power minus 1 by n. So we get this equation. Now this index is 1 and this index is 1. So we can add these two index. So we get 1 minus 1 upon n is n minus 1 upon n. So final equation reduces to n upon n minus 1 P1 V1 into bracket P2 by P1 to the power n minus 1 upon n minus 1. This value and this value, they are just reciprocal. We can modify this P1 V1 again by MRT1. Final equation I got is n upon n minus 1 MRT1 into P2 by P1 to the power n minus 1 by n minus 1. This is the equation for work done neglecting the clearance. So just now we have developed two equations for the equation for compressor as n upon n minus 1 P1 V1 P2 by P1, these equations. So this equation is basically for without clearance. We will try to find out the equation for this one is with clearance, is area of this figure and area of this figure. Both this figure represents without clearance, so we can calculate area 1. The work done 1, 2, 3, 4 is given by 1A, 2B, 4, 3, AB. This equation we can write from this equation, and we have to just substitute for N1, N2. So what we get is, we will assume here this equation cannot be solved, so we have to assume N1 and N2 are same index. Then we can solve this equation. So the bracket is remains same. P1 is common, so only different quantities V1 minus V4. What we get is n upon n minus 1 P1 V1 minus V4 into bracket P2 by P1 to the power n minus 1 upon n minus 1. Now we already proved here that mass equals to P1 upon RT1 into V1 minus V4. So we will replace this P1 V1 minus V4 equals to M into RT1. Equation, that is N upon N minus 1 MRT1 into P2 by P1 to the power N minus 1 upon N. This is the expression for work done in case of clearance. But if you observe the equation of this, that is with clearance, that is equation number 1 and equation number 2, they are same. It means that the clearance has no role on the work done. So this can be asked as a proof, and we can very well prove that equation number 1 and equation number 2 are identical. So clearance has no role on work done. So by this time we have developed two important equations. One is m dot and second is work. If you multiply this work with n by 60, then it becomes the power. So this is called as indicate power and is represented by W dot. I will call this as IP. So work done will be equals to N upon N minus 1 M into RT1 into P2 by P1 to the power N minus 1 N upon N minus 1 upon N minus 1 into N by 60. Remember, this equation is applicable to both. If I make this is M dot, then this equation will be cancelled out as N by 60 because N by 60 is included here. So this is the final equation you must remember. So up till now we have developed two equations. One is for mass flow rate and one is for power. This equation is applicable to both for single acting as well as double acting, and this equation is also applicable for both single acting as well as double acting. So normally you make equations which are useful for both, but it does not matter it should be a single acting or double acting. In this video we will going to develop the equation for volumetric efficiency based on suction conditions, that is P1 and T1. So at this point your suction valve opens, at this point your suction valve closes. So this one is called as actual capacity of compressor and this one is called as theoretical capacity. Volumetric efficiency is defined as the ratio of actual capacity to theoretical capacity. It is a true definition of volumetric efficiency. It is given by V1 minus V4 upon Vs. To solve this equation further, we will start with point number 3. The volume at point number 3 is same as Vc and 3 to 4 is a polytropic expansion. Let's call this as equation number 1. So we have pressure at point number 3 is P2. So we have P2 V3 to the power N, and point number 4 is pressure is P1. P1 into V1 to the power 4. Index is N2. That is the index of expansion. We can solve for V4. And V4 equals to V3 into P2 by P1 to the power 1 by N2. Now this V3 is same as Vc. So we can write this V4 as Vc into P2 by P1 to the power 1 by N2. In addition to this, we defined one ratio called as clearance ratio. Clearance ratio is equal to Vc upon Vs. This is usually 3 to 5%. And finally, we have the volume V1. This volume V1 is consist of two volume. One is Vc plus Vs. So we will replace V1 equals to Vs plus Vc and V4 equal to Vc. We will put in equation number 1. So V1 is replaced by Vs plus Vc. V4 is replaced by Vc into P2 by P1 to the power 1 by N2 and is divided by the Vs. So each term is divided by Vs. What we get is 1 plus Vc by Vs, which is same as clearance ratio, minus Vc by Vs is again a clearance ratio, is P2 upon P1 to the power 1 by N2. So eta wall is a strong function of clearance volume and the pressure ratio. At high altitude the pressure P1 will decrease, so this quantity will increase and therefore eta wall will decrease. So at high altitude we conclude the suction pressure will decrease, therefore volumetric efficiency will increase. Second minus V4 upon Vs, and alternate form of this equation is this one. So this is the third formula that we have developed for the volumetric efficiency. First is m dot, second is w dot, and third is eta wall. I will collect all these formula. So eta wall equals to 1 plus C minus C P2 by P1 to the power 1 by N2. By default N2 is same as N1. N2 is index of expansion and N1 is the index of compression, and is same as V1 minus V4 upon Vs. From Vs we can calculate the dimensions of cylinder. So this formula is used to calculate for dimensions of cylinder. Number of times the manufacturer is somewhere different than where we have to apply where we have to use the reciprocating compressor. In that case we required another definition, that is called as volumetric efficiency based on the atmospheric condition. To equate the mass at the given suction condition, that is P1 into V1 minus V4, same mass at the suction condition and atmospheric conditions. So if we equate by ideal gas equation and we can solve for eta vol at V1 minus V4, we get, so the volumetric efficiency based on the ambient condition is given as V1 minus V4 at atmospheric upon Vs. This is also called as atmospheric. So if we replace V1 minus V4 atmospheric from these two equation, your R is cancelled. V1 minus V4 is same as our original V1 minus V4. We have this value is P1. This value of P atmospheric will come here, denominator. This one is T1 and this one is T atmospheric. So T atmospheric come in numerator and this one is T1 and this whole thing is divided by Vs. So definition used for eta vol atmospheric is eta vol into P1 upon P atmospheric into T atmospheric upon T1. Remember, this definition is not used to find out the dimensions of cylinder. Only this definition is used to find out the dimensions of cylinder. Now we will discuss the two important terms. One is called as isothermal efficiency and isentropic efficiency. For this one I will consider a PV diagram neglecting the clearance, because we already proved that the work has no role for the clearance. 1 to 2 dash is isothermal process, and isothermal process the index n equals to 1 is represented by PV equal to constant. PV is equal to constant, so value of n equals to 1. So area under this diagram we can find out as W iso, which can be again find out W iso equals to integral of minus VdP. And for the isothermal process we have PV equals to constant, so we can write this equals to integral of minus C by P dP from 1 to 2. Pressure P1 to P2 we get equals to minus of C into ln of P2 by P1. C can be written as mRT1 into ln of P2 by P1. So this one is work done for isothermal process, and if you want to find out power, you just make a dot, so this will become power. To find out the isentropic work, we will use the same equation that we have given here, that is W dot equals to, for isentropic processes, instead of n it should be gamma minus upon gamma minus 1 m dot RT1 into P2 by P1 to the power gamma minus 1 by gamma minus 1. We can represent the W isometric process is 1 to 2 dash, and the work done required for this process is area under 1 to 2 dash, 3 and 4. Then for polytropic process we have work done equals to 1, 2, 3, 4, and for isentropic, to conclude this we define the free air delivery, which is defined as, so FAD is defined as amount of air delivered by compressor and usually expressed as meter cube per minute at atmospheric pressure and temperature. I denote FAD simply by letter FAD, but my unit is meter cube per minute. This is a standard unit, is meter cube per minute. So we can calculate mass from this, that is the mass flow rate. It is expressed at atmospheric, so it's a P atmospheric multiplied by FAD by 60, which will take care of meter cube per second divided by RT atmospheric. So this is the definition of FAD, and from FAD we can calculate mass flow rate. From mass we can calculate V1 minus V4. From V1 minus V4 using eta vol we can calculate Vs. From Vs we can calculate dimensions. So these are the equations that is normally used. One is for m dot, which take care of both single acting and double acting. One is for W dot, that is polytropic power required. If you divide by m dot we can get out specific work. This equation is for volumetric efficiency, 1 plus C minus C, V1 minus V4 upon Vs, used to normally calculate dimension cylinder. W iso is given by m dot RT1. If you want specific work, just divide this number by m dot. It is the equation for isentropic process. And one more equation, that is eta iso is W iso upon W poly. Reason is very straightforward, that the work required for isothermal is small as compared to W poly, and eta poly is W poly upon W isentropic, because this work required for polytropic is less than W isentropic. And one of the important definition is air delivery, which is normally get confused by students, is m dot equals to P atmospheric into FAD by 60. upon RT atmospheric. This one is kg per second. Some important definitions that is normally used for single acting reciprocating compressor.